The method of open circuit time constant to find FH for a CS amplifier for which GM is equal to 1.5 milliampere per voltage, CGS is equal to CGD, which is equal to 0.2 picofarad, RO is equal to 20 k ohm resistance, RL is equal to 12 k ohm resistance, Rsig is equal to 100 k ohm resistance. Okay, so we have all these value provided, and the question is asking for to find out find the FH value for the following cases when CL is equal to 0, CL is equal to 10 picofarad, and CL is equal to 50 picofarad. And we have to compare that one with using, we have to find this one also using the Miller approximation method, and we have to compare the values. Okay, now let's do this. So first of all, using the open circuit time constant method, the way to find FH, the 3 decibel frequencies, by losing this equation. FH is equal to 1 over 2 phi tau h. This tau h is the time constant. Okay, this is what we have to calculate. This tau h consists of 3 time constant added together. One is CGS times Rsig, this is one of the time constant, plus the next one is CGD times Rsig times 1 plus GM RL prime, and then plus RL prime. This is second time constant, and then the third one is CL times RL prime. Okay, this is third time constant. So we have to add these 3 time constants to obtain this tau h time constant. So let's go ahead and calculate. Since we have all the values readily available, we have to just plug it in and find the answer. So here CGS value is provided to us, that is 0.2 picofarad. So 0.2 pico right here, and then Rsig is provided to us, that is 100k. 100k right here, and then what else do we need? Okay, that is for the first one, and then CGD, that is also 0.2 pico. Plug that one here, and then Rsig again 100k, and then times 1 plus GM is also provided, that is 1.5 milli, and then RL prime is okay. We don't have the RL prime, so we have to calculate the RL prime. We have the RL provided and also RO provided. RL prime is nothing but RL parallel to RO. So this is basically the product over sum. In this case, RL is 12k, and then RO is given to us, that is 20k. So which means 12k times 20k over 12k plus 20k, product over sum. Okay, and if you calculate this value, you're going to end up getting RL prime to be 7.5 kilo ohm resistance. Okay, so that is this one. And once we have this one, we can plug it in here. So we have the RL prime also available, that is 7.5k right here, and then close this bracket, and after that we have plus RL prime, that is 7.5k again, and then close this. And then in this case, CL for the first case is 0. I'm doing the A part of this. For the first case, CL is 0, which means CL RL prime, that term will be completely gone, because 0 multiplied by RL prime, that's 0. So that's going to be 0. Then we have to just calculate this value. If you calculate this value, you're going to end up getting 266.5 nanosecond. Okay, then once you find out that, you have to just plug it in this equation. FH is equal to 1 over 2 phi tau h. Let's go ahead and plug it in. So we are going to find out the frequency FH, which is equal to 1 over 2 phi tau h, and okay, so 1/25 tau h is 266.5 nanosecond. 1/25. Okay, 1/25 times 266.5 nanosecond. And if you calculate this FH value, you will end up getting 597 kilohertz. Okay, that is the first case in the A part when CL is equal to 0. When CL is equal to 10 picofarad, B part, the only difference is everything remains the same except this CL/RL prime. Now we are going to have the CL/RL prime term as well. So if I just copy this, I can just copy and paste it and add that term. Okay. Control-C, and I'm going to copy paste here. Okay, here the only extra thing we are going to have is initially we didn't have CL/RL prime for the first case, but now in this case we are going to have the CL/RL prime. So we have to add that one with whatever we have this one here. So here they have provided that CL for the second case to be 10 picofarad. So we are going to have 10 pico right here, multiply by the RL prime, that one we calculated right here, 7.5K. Okay, and we have to just calculate this value, and if you calculate it, you're going to end up getting 341.5 nanosecond. So once you have tau h, again same equation, that is FH is equal to 1/25 tau h, and then 1/25 times the tau h value we calculated, 341.5 nanosecond, 341.5 nanosecond, and then if you calculate this value, you're going to end up getting 466 kilohertz. Okay, so that is for this one. And then the next one is C part. In the C part also exact same thing. The only difference is we have load capacitance right here, so it means this only term extra is going to come there. So I can do the same thing right here, copy again, paste it, and for the last part, okay, you know what, I'm gonna erase this one. Okay, paste it here. Put the C over here. So the only difference again is we are adding the load capacitance and multiplying that one with CL that is given for the C part. C part is 50 picofarad. So 50 pico right here, multiplied by the RL prime, which is nothing but 7.5K. Okay, and for this one, if you calculate this one, you're going to end up having the time constant to be 641.5 nanosecond. And again, FH value is nothing but 1/25 tau h. In this case, 1/25, the tau h value we calculated is 641.5 nanosecond, 641.5 nano. And if you calculate the frequency, you're going to end up getting 248 kilohertz. Okay, so these are the values we obtained when we use the open circuit time constant method. So in the A part, we got the FH value to be 597 kilohertz, and in the B part we got the FH value to be 466 kilohertz, and in the C part we got the FH value to be 248 kilohertz. And then they are asking compare with the value of FH obtained using the Miller approximation. The difference between open circuit time constant and Miller approximation is, in the Miller approximation this CL term doesn't come into play. That's why for the Miller approximation it's going to be just one solution, because we don't have the three, we are not going to have this three situation, because the load capacitance is not used at all to calculate the FH value in Miller approximation. So if we calculate FH value in Miller approximation, the equation is this: FH is 1 over 2 phi C in times the Rsig prime, and in this case 1 over 2 phi C in value is not readily available, so we have to calculate that one. So to calculate the C in, we have to use this equation, that is CGS times CGS plus CGD times 1 plus GMRL prime RL prime, and that's it. And that one multiplied by the Rsig prime, and now we have to plug it in the value. So 1 over 2 phi times CGS value, that is given to us 0.2 picofarad, 0.2 pico, and then CGD value is CGD value is nothing but same value, 0.2 picofarad, and then one plus GMRL prime. So that one should be multiplied with this. Since I don't have space, I'm gonna continue over here the multiplication. Oh, you know, I better bring it to next page because we don't wanna misunderstand this. So maybe I copy this and bring it to next page. Okay, so here plug in the values: 1 over 2 phi CGS. CGS value is nothing but 0.2 picofarad. CGD also same, 0.2 pico. 1 plus GMRL, which is GM is 1.5 milli, and RL prime we calculated right here, that is 7.5 K. Okay, then that one multiplied by the Rsig prime. And in some cases Rsig prime, if in the question they provided R phi and Rx, you need to calculate the Rsig prime, because when you provided R phi and Rx, that is like R phi parallel Rx plus RB parallel Rsig, so you have to calculate Rsig prime like that. And also if they provided beta and GM, you have to calculate R phi value. But here if nothing provided, then Rsig is the Rsig prime. So in this case the Rsig prime is just 100K. Okay, so if you once you have all of them, then you have to plug it in and calculate the value, and if you calculate, you're going to get 600 kilohertz value. And if you compare this value, this is, we calculated this one using Miller approximation. We did the same thing using open circuit time constant method with 3 different load capacitance. In the first one, when the load capacitance 0, we got the FH value to be 597. When the load capacitance is 10 picofarad, we got the FH value to be 466 kilohertz, and when the load capacitance is 50 picofarad, we got the FH value to be 248 kilohertz. But for the last one, it doesn't matter what load capacitance you have. You may have 0 load capacitance, 10 picofarad or 50 picofarad. You're going to get 600 kilohertz all the time, because the load capacitance doesn't come into play when you use Miller approximation to calculate the FH value. So if you compare this value with the A part of this, it's almost close to it, because in the A part the load capacitance is 0, so it's almost like it's not considered. So 597, and here also 600, almost close to it. So when we are using Miller approximation, it's like we assume just load capacitance will be 0. Okay, that's why if you have load capacitance and if you want to calculate the FH value, the best method is open circuit time constant method, because that's gonna give the more realistic value. And that's it for this video. I hope you guys found this video helpful. Thanks for watching. Don't forget to subscribe my channel. See you guys on my next video.